Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the grand tapestry of scientific thought, certain threads possess a tensile strength that reweaves the entire fabric of understanding. Theodor Schwann's 1839 treatise, Microscopic Untersuchungen über die Übereinstimmung der Struktur und dem Wachstum der Tiere und Pflanzen, or Microscopic Investigations on the Accordance in the Structure and Growth of Animals and Plants, represents one such revolutionary filament, published in a period when biology was a fragmented collection of descriptive disciplines, adrift between the lingering spectres of vitalism and the hard certainties of physics and chemistry. Schwann's work offered a unifying principle of extraordinary elegance and power. It was an intellectual achievement that elevated biology from a state of organized observation into a coherent science, positing a single, concrete, and observable entity as the basis of all living things. Through a meticulous campaign of comparative microscopy and audacious analogical reasoning, Schwann erected the cell as the elementary particle of life, a concept so foundational that its establishment marks a caesura in the history of the life sciences, dividing all that came before from everything that would follow. His work, while containing a famously fruitful error regarding cellular origin, provided the essential framework upon which the entire edifice of modern biology, from histology to pathology to molecular genetics, would be constructed. The intellectual landscape into which Schwann introduced his theory was one of burgeoning potential and profound conceptual disarray. The preceding decades had witnessed a critical technological maturation in the primary tool of his inquiry, the microscope. The innovations of Joseph Jackson Lister in the 1820s and Giovanni Battista Amasi had largely vanquished the chromatic and spherical aberrations that plagued earlier instruments. This conquest of optical distortion transformed the microscope from a device of amusement into an instrument of precision, capable of revealing the intricate substratum of organic tissues with unprecedented clarity. Early observers, from Robert Hooke with his description of cork cells to Antony van Leeuwenhoek and his animalcules, had glimpsed this microscopic world, yet their findings remained a cabinet of curiosities. Their observations were atomized, lacking a synthetic theory to connect the fibrous architecture of a plant stem with the gelatinous substance of an embryonic animal. The prevailing intellectual currents were equally fragmented. German native philosophy sought grand, often speculative, unifying schemes derived from idealistic principles, while a growing contingent of researchers, coalescing around figures like the formidable Johannes Müller in Berlin, championed a more empirical, physiological, and mechanistically grounded approach to understanding life. Schwann, a gifted student within Müller's orbit, was steeped in this ethos of rigorous experimentalism. The immediate catalyst for Schwann's grand synthesis arrived during a now legendary dinner conversation in October of 1837. His friend and colleague, the botanist Matthias Schleiden, had the previous year published his own pivotal paper, Beiträge zur Phytogenesis, or Contributions to the Study of Plant Origins. In it, Schleiden argued that all plant tissues were composed of cells and, crucially, that the formation of a new cell centered upon the nucleus, a structure he termed the cytoblast. As Schleiden recounted his findings, a powerful intuition seized Schwann. He recalled his own recent observations of the animal notochord, or chorda dorsalis, where he had seen similar structures containing nuclei. The question became electric. Could the principle Schleiden had identified in the plant kingdom be the universal law of organic development? This query provided the research program for microscopic investigations. It was a moment of profound intellectual cross-pollination, where a specific botanical insight became the key to unlocking a general biological truth. Schwann immediately set out to test this hypothesis, leaving the dinner table to examine his animal specimens anew. Now armed with a powerful guiding eye, the Microscopic Investigations is, at its core, a masterpiece of comparative anatomy conducted at the microscopic level. Its argumentative structure is methodical and persuasive, designed to lead the reader from the most unambiguous evidence to the most comprehensive conclusions. Schwann begins his empirical survey with tissues where the cellular nature is most apparent, wisely selecting cartilage and the embryonic notochord. In these tissues, the constituent cells are discrete, suspended within an intercellular matrix, their individuality beyond dispute. He meticulously documents their structure, a containing membrane, a fluid content, and the ever-present nucleus, confirming Schleiden's prerequisite. From this solid foundation, he embarks on a systematic march across the animal kingdom's diverse tissues, a journey that was both technically demanding and conceptually audacious. He demonstrates the cellular composition of bone, where osteocytes reside within their lacunae of connective tissue, with its fibrous elements originating from cells of muscle, whose fibers he interprets as fused cells, and even of nerve tissue, where he identifies the sheath surrounding the axon, a structure that now deservedly bears his name, the Schwann. This empirical tour de force culminates in two foundational propositions that constitute the heart of his cell theory. The first is the universality of the cell as the basic unit of structure and growth. There is one universal principle of development for the elementary parts of organisms, however different, he asserts, and this principle is the formation of cells. This declaration swept away centuries of perceived difference between the kingdoms of life. The leaf of an oak, the feather of a bird, and the brain of a human were, at their most fundamental level, constructed from the same elementary particles. The second proposition extends this structural unity into the realm of function. Schwann argues that the life of the whole organism is the sum of the lives of its individual cells. The cell is the locus of all vital phenomena, from metabolism to irritability. In a stroke, he dissolved the mystique of a holistic vital force animating the organism, relocating the processes of life to a tangible, observable, and material unit. The plant and animal kingdoms were reunited under a single, microscopic ban. Yet, within this revolutionary synthesis lay a significant and highly instructive error. Schwann's theory of cytogenesis. In seeking a mechanistic explanation for the origin of new cells, he adopted and elaborated upon Schleden's model of free cell formation. He proposed that cells arose de novo from an unformed, nutrient-rich liquid he termed the cytoplasma. In a process strikingly analogous to crystallization, he envisioned a nucleus precipitating out of this organic fluid, followed by the gradual condensation of a cell membrane around it. This hypothesis was powerfully attractive in the intellectual climate of the 1830s. It offered a purely physico-chemical explanation for generation, sidestepping any reliance on pre-existing vital structures and aligning biology with the triumphant explanatory models of the physical sciences. It was an elegant attempt to explain creation without recourse to a continuous, unbroken chain of life. The limitations of the era's microscopy made direct and sustained observation of cell division a rapid and complex process, exceedingly difficult, lending a degree of plausibility to the more static, precipitation-based model. This error, inherited from botany and generalized across all of biology, would become the very point of contention that spurred the next great advance in cellular science. The immediate reception of the microscopic investigations was overwhelmingly positive and its impact transformative. Johannes Müller, Schwann's mentor, recognized its significance at once, hailing it as one of the most important discoveries of the age and incorporating it into his influential textbook on physiology. The work resonated across Europe, with an English translation appearing in 1847 through the prestigious Sydenham Society, ensuring its rapid dissemination. Throughout the scientific world, the conceptual clarity it provided was immense. The fields of histology and embryology were reborn on cellular foundations. The bewildering diversity of tissues could now be classified and understood as communities of cells. The development of an organism could be traced from a single fertilized egg, the zygote, through successive generations of cellular proliferation. The cell theory provided a common language and a shared object of study for botanists, zoologists, physiologists, and anatomists, effectively dissolving the artificial boundaries between them and catalyzing the emergence of biology as a unified discipline. It provided a material basis for heredity and disease, creating the conceptual space for the disciplines of genetics and pathology to flourish in the coming decades. Schwann had handed his contemporaries a biological equivalent of the atom, a fundamental unit that promised to rationalize the complexity of the living world. The long-term legacy of Schwann's work is a testament to the dynamic nature of scientific progress, which proceeds through both brilliant synthesis and rigorous refinement. The flaw in his theory, the doctrine of the cytoplasma, became a powerful engine for further research. Throughout the 1840s and the 1850s, improved microscopic techniques and more patient observation are researchers like Robert Remack, an investigator whose genius was long underappreciated, and Albert von Kerlicke, provided mounting evidence against free cell formation. They observed cells, particularly in embryonic tissues and blood, undergoing a process of division, appearing to arise directly from the cleavage of parent cells. This line of inquiry reached its definitive culmination in the work of Rudolf Virchow. In his seminal 1858 publication, Die Cellular Pathologie in ihrer Begründung or Physiologisch und Pathologisch Duobelea, or cellular pathology as based upon physiological and pathological histology, Virchow directly challenged and disproved the cytoplasma theory. He codified the principle of cellular continuity in his enduring aphorism, omnis cellula e cellula, meaning all cells from a cell. Virchow's work was a profound correction, but it was a correction made possible only by the foundation Schwann had built. Virchow did not discover the cell, he inherited it from Schwann. He took Schwann's static, structural unit and imbued it with a dynamic, genealogical history, showing that every cell is a descendant of another cell in an unbroken lineage stretching back to the dawn of life. The cell theory was complete. In conclusion, Theodor Schwann's microscopic investigations remains a landmark of biological science, a work of profound synthesis that redefined the very object of its study. By marshalling evidence from across the living world with systematic rigor, Schwann demonstrated that the cell was the universal architect of life, the common denominator linking the simplest alga to the most complex mammal. He provided biology with its fundamental unit of analysis, transforming it into a modern, unified science. His theory was a powerful solvent for the lingering ideas of vitalism, grounding the phenomena of life in a material, observable entity. While his explanation for the origin of cells proved to be a magnificent and productive error, it perfectly illustrates the self-correcting mechanism of science, as its refutation by Virchow and others completed the cellular paradigm that Schwann had initiated. He stands in the pantheon of science as a unifier, an intellectual architect who perceived a universal pattern amidst bewildering diversity. With his microscope, he looked upon the tissues of animals and plants and saw a shared secret, a fundamental accordance, that forever altered our understanding of what it means to be alive. His 1839 treatise is the birth certificate of modern biology, the moment the microscopic world was shown to possess a grammar, and Theodor Schwann was its first and most eloquent grammarian.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.